Okay, here we are going to be taking a look at how we could use a, say, table or a graph to determine at least one solution of this equation that we see here. And what we see here is, as a matter of fact, some third degree polynomial, but notice that we've set it equal to 0. So typically we have f of x equal to the polynomial, which I'll actually write this out here, x cubed plus 2x squared minus 5x minus 6. But what we're specifically saying is we want to find the solutions to this equation that actually cause our y value to be equal to 0. So that being said, recall that when we're finding the x values that cause our y value to equal 0, we're really looking for the x-intercepts of the graph, or that our solutions are the x-intercepts of the graph. So what we're going to do is, once we think we can determine an x-intercept of our graph or a solution of this equation, then what we're going to do is we're just going to use synthetic division to verify that it actually is a solution, that it does actually, when you plug it in, cause this to be 0, and then we're going to use that fact to solve this polynomial equation. So again, our focus is on the fact that anything that causes this equation to be true here really are just x values that cause our y value to be equal to 0. So that is to say that we are going to say that solutions to a polynomial equation, or solutions to the equation, are the x-intercepts of its graph. And so we have this third degree polynomial here, and so it looks like we can only see on this graph here, and at least what we've been given here is a window that goes from 0 to 4 on the x-axis. It looks like we're going by 1, so we have 1, 2, 3, 4, and on our y-axis we're going from negative 25 up to 25, and it looks like it's going by 5s here. So in terms of, do we think we see any zeros or solutions or x-intercepts of this polynomial equation? And I kind of feel like I see one right here. I think it feels like it's obviously x equals 2 would be something that when I plug it in, I get a y value of 0. So the way we're going to check this is we're actually going to set up our synthetic division here, our synthetic division array. We have a 1, a 2, a negative 5, and a negative 6. And because I feel like x equals 2 is a solution, then what I'm going to see are two things. One, when I plug my 2 in here, I'm not going to get a remainder whatsoever. Okay? And 2, when I plug my 2 in, I'm going to get a y value of 0. So you can kind of see that getting a y value of 0 at that x value goes hand in hand with the fact that if we were to divide by the factor x minus 2, and I'm getting that from over here where if I were to move the 2 back over, this would have been the factor. But basically it's going to mean that x minus 2 must have been a factor of this if it went in evenly with no remainder. And so let's take a look at what we get here. We think that 2 is a solution. Here I am saying 2. I need to write a 1. So we get 2 times 1 is 2. 2 plus 2 is 4. 2 times 4 is 8. 8 plus a negative 5 is a negative 3. And 2 times a negative 3 here is a negative 6. And I get 0. So just to go back and check my signs here to make sure that I haven't missed anything. We got 1, 2, negative 5, negative 6. 2, 4, 8. Oh, there it is right there. Positive 8 and a negative 5. You guys, I must be tired. It's a positive 3. So we get a positive 6 and then a 0. So a few things that we want to say about this. First of all, we want to show that, hey, dear audience, 2 is actually an x value that when you plug it in, you certainly do get 0 for a y value. And so that means that it would be a solution of this. Furthermore, if x equals 2 is a solution of this, okay, we want to find all of the solutions here. We say solutions. Then what we would say is then x minus 2 would have had to have been a factor. And the only reason I mention that is because when you divide something, let's put it this way. If I were to take x cubed plus 2x squared minus 5x minus 6 and divide it by x minus 2, what I get left with is a quotient, but specifically a quotient that has no remainder. And in this case, we can see that our quotient here is x to the second plus 4x plus 3 plus no remainder whatsoever. So the thing that I want you to consider is this. If this truly is x squared plus 4x plus 3, then the fact that we divided this out and left behind this other quotient right here would mean that the other factor is this right here. We could say that literally our original polynomial equation was equal to what we got for a quotient times the thing we would divide it by. And so if we're going to find all of the zeros of this, essentially what we're going to be doing is saying, well, okay, well, if this times this comes back together to be the original thing, and x minus 2 is a factor, then maybe we could find the other two zeros hiding in this by factoring it as well. And so, long story short here, we've got, the fact is 2 was a 0. And because 2 was a 0, we got left with this second degree quotient here. We wanted to find the other two zeros. And so we'll set it equal to 0 and solve it. But we can see that this actually is very easy to solve just by factoring here. X plus 3, x plus 1 equals 0. And if that's the case, then either x plus 3 equals 0, which means that x equals negative 3, or x plus 1 equals 0, which in that case would mean x equals negative 1. And so what we get here is we get 2, negative 3, and negative 1. And we got each of those answers each one time, so they each have a multiplicity of 1, which kind of makes sense here now that we look at this graph here. Because 2, we only got it for an answer once, or it has a multiplicity of 1, that is an odd multiplicity, which we know means if you have an odd multiplicity, that your graph is actually going to cross at that x value right there. Okay, cheers.